Welcome to a new test and teardown video. This time we're going to look at this oscilloscope from Radiometer. And this one is the model OSG41a. It is from about 1951. Says the schematic. It is nicely dated. Wow, 1951. It is very big, as you can see. Let's try and zoom out and compare it to any other normal instruments. It takes the entire table. It is really, really big. It says in the manual, this one is 57 centimeters deep, 31 centimeter wide, and 40 centimeter high. And the weight is 28.6 kilos. So there's a super hefty handle here. And even that, you can't really walk long with it. It feels like your fingers, they're like ripped out or something like that. So it is definitely not a one-hand lift. It should use about 175 watts, and it's of course completely tube-based. We got a few really cool features. So this is the on-off switch, this one here. And you would normally use the 2 kilowatt anode supply, but if you take it to the 4 kilowatt, you get more intensity, you get a much faster beam, and this is for low light application where you are running really, really fast. And this is only a 1-channel 5 megahertz oscilloscope, and the connectors for channel 1, and this is for the Y. So this is the vertical deflection input, and the horizontal sweep, also called X. You can have all sorts of external inputs. That will be the connectors here on the side. Amazing idea. I can't forget about it. You know, the connectors on each side like that. How cool is that? But we need to open and have a little visual inspection before we get to it. I'll be all the different trigger things and the variable sweep frequency, all the different horizontal sweeps and all that. Oh yeah, by the way, if you don't like this, you can pull this up and get full access to the screen. It's really, really big. In a beautiful condition. I don't see any holes or marks or anything like that. Normally on really, really old scopes like this, you will have a dark line here in the middle, but that is not the case with this one. So that is really, really good. Getting the scope out of the case seems to be a little bit difficult. I even had to consult the manual. It says all you have to do is remove the 2 screws and the handle, and then you can pull out the scope from the cabinet. But it's like not easy. Obviously it weighs just under 30 kilos. So this massive weight presses down onto this bottom metal, preventing you from pulling it out. And like, how do I do this without getting injured as well? It is just amazing, this oscilloscope. Let's get a lot of light here so we can see the different layers. Of course, they made a real thick chassis frame in here and welded everything together for stability. Look at that. And then we got, this is 1 millimeter bent metal like that. And the way that it is bent and the way that it folds in there and goes up here and is screwed to the back of this frame, it adds a crazy amount of stability to this big and heavy oscilloscope. I am still walking around my visual inspection. So far, I figured out all this here is the vertical amplifier, and we got 3 tubes here and three more down. Oh, I can't even lift it like that. And 3 more down there. So that will be differential stages. 3 differential stages made by pentodes to create all the gain we need for the vertical amplifier. That's a little rectifier for the power supply, the 300 volt power supply. So there's a GC34. The fun thing is, schematic says it's a 32 or 31 or something like that. So this is a little bit different. Funny place to put that one, by the way. We got a little bit of corroded fuses, not looking too good, so I need to go through all that as well. That will be the voltage selector. I kind of like that voltage selector. It's really good and easy to understand. So far so good. And here is the horizontal amplifier. We only got 2 stages, again differential amplifiers made by pentodes. So you see here's the final and the final. PEEL.DK, exactly the same as the vertical amplifier, and then EF80 pentodes. So we got 1 here and 1 here, and that will be the 4 tubes in the horizontal system. And I bet this is not normal. So there's a completely loose hanging, desoldered from overheating somehow. So I need to figure out where is this supposed to be mounted. So I need to consult the schematic a little bit. This is interesting. And that will be the high voltage supply, the regulated 300 volts. And here is, of course, the sweep system. Again, everything is made using tubes. And that is, of course, so impressive. If you look in here, this capacitor right there, see the top? This looks a little bit suspicious, this corrosion. I already added a little marker here. This is something I need to look a little bit more at. Let's see if I can get some light to shine on this capacitor. See, that is cracked. This can't be good either. Yeah, and a little repair flying capacitor here. So there's definitely this yellow capacitor lost some of its good things. So they just added another capacitor in parallel just to solve the problem for now. And here is the back side of this rectifier tube. And this funny corrosion or whatever it is making me a little bit nervous. And also the corrosion here on the tube holding piece. Why is that so corroded? And everything else seems to be quite all right. How is that possible? So now I have flipped the scope around so we can see the vertical deflection amplifier is here. And again, the capacitor with a little bit suspicious looking aluminium here. And one of the tubes in this deflection, again, is looking really suspicious with this white funny looking. Oh, okay, maybe this capacitor here is not looking healthy. See, this looks like leaked acids. So it went out here at the top and then was going around the capacitor inside this plastic. Look at that. Nasty, nasty. That will be the high voltage transformer, and the rectifiers for the high voltage is of course also made with 2 high voltage diodes right there. And we got some real big hefty capacitors in here. Look at that baby. What exactly is going on with the way this wire looks up there? Is this good? That needs a little bit of attention here. This is interesting. This can't be right. Really? It looks like the wire is not correctly mounted. So it's just going through. And then screwed in here. What is the... really? Yeah, here's the funny thing. Look at the distance. I think it's touching. Yeah, there's a mark. I keep finding things to worry about in this one. So I flipped it on the side, and this is of course a little problem because we got those connectors at the side. So I just figured, okay, we just put some screwdrivers. That is really perfect. But look at that. Of course we got focus and intensity, and those 2 potentiometers, they are at about minus 2000 volts potential. And it also reveals here, look how they mounted the potentiometer at super nice and safe isolation distance to chassis. Oh, this is super good. Wow, thinking about it. But this piece of metal right here is the shaft that goes all the way to the front panel. And look at that. Of course, it touches the metal to the front panel. This is good safety. That means it will be 0 volts on this shaft, and it's not going to kill anybody touching this one. Whatever, right? But here it goes. So here's 0 volts, and here is minus 2000. What kind of safe distance is there here? And you can even see the little sparky. Look at that. So I bet this is more or less skipping over here, right? And again here, let me try and turn the... Yes, exactly. Let's try and focus on exactly that point and get some light. Why don't you want to focus exactly where I want you to do it? What kind of nasty is this? Where's that coming from? This is the on-off switch. And then the 2 kilovolt or 4 kilovolt anode voltage. Well, this is not exactly what happens. I will show the schematic later and show exactly what is going on. But here is this anode voltage switching, and you can definitely see all this high voltage is what attracts all this. But they've made a really, really nice mains switch with this mechanical interface here, and that works perfectly fine. Look at that. And then clickety clickety. Lovely. I kind of like that. Is a sexy way to do it. Look at all those big hefty transformers. That's the inductor for filtering. That will be the normal transformer, but it's only using 175 watts, and there you have it. Those 2 big transformers. So I am cleaning all the high voltage stuff here. Real nice and fine, and removing all those little over voltage whiskers. So all that is nice and shiny. And then I realized the on-off switch and the high voltage here was just so dirty. It was completely splattered into some nasty, sticky. Everything here was like really nasty and sticky. What happened? I still cannot figure that out. But this entire high voltage switching here was totally black. Now it's nice and shiny. And here is the rectifier. Look at those resistors. That will be the output series resistors. Look how burned and nasty they are looking. So I bet they are running a little bit warm. They're supposed to look like all the other red resistors. Like that, right? This is not too good. I'll try and see if I can clean them, and maybe they still have the right value. I can of course check that with the schematic. See this acrylic here. Acrylic is really good for high voltage, but it's really dirty. And this is not good for high voltage. So we want clean. I now know what is the reason for all this black, dirty, slimy stuff that is all over the place. And if we look a little bit on this type of capacitor right there, this is an oil-filled capacitor. This one where I shine right now. And we got another one in here. I don't know why it is impossible to focus on these. It's just impossible. But anyway, the one in the middle here is completely wet and gross, and it went all the way down here, and then it dripped through these holes and all over the place down here. So I don't know exactly what to say. All this stuff here would be the high voltage. Other than that, I changed this cracked capacitor up here. And the two resistors on the other side, I showed this earlier in the video. I removed one of them because they're not on the schematic, this extra resistor. So let's try and power this thing up. So what I want to do is I want to give it just a little bit of voltage. And yes, we don't have a short. So I'll slowly crank it up, and then we'll see what happens. We should start to see some Can we see a little bit of Yeah, we got a light here. I put everything here in the middle. And this is 96 volts, and it's using 27 watts. So all we have to do is slowly crank it up. I don't see a lot of filament going on. So the 222 volts, and it's using 133. So this is the sweep generation. No. Well, I will be back. So I now know why I didn't have a beam, and of course I had the deflection going all the way around, completely unsymmetric. And why is that happening? The power supply, let's look a little bit here on the power supply schematic. We got a little 85 volt reference voltage tube here, and then it goes to the EF80 tube, and that pentode is a like a voltage feedback system. So it measures the output voltage and it uses the reference voltage, and then it controls the output power pentode. And if we look here at the schematic, we can see it's called PEEL.DK. And I did not have 85 volts. I only had like 40 volts on this reference tube. So I tried to change the voltage tube, and that didn't change anything at all. So I also tried to change the EF80 tube. That did not change a lot, a little bit. But now I just added another, we can see there's a pull-up resistor that adds some current through this tube. And I added just one more in parallel. And now my voltage here is at least 65 instead of 85. But that voltage is now high enough so I will get a regulation and I will get an output voltage. The 160 volts is, I think it is 120 volts. But at least it is good enough to get this up and running. And if we go back to the unit here, we will see that in my unit, there is not a PEEL.81. No, it's an EL.81. So this one was probably changed by somebody. And the difference between EL and PL, that is the filament voltage. So what they did is, this yellow wire here is the filament. So they lifted the two wires for the filament. You can see the two brown wires in there. They are lifted. So that will be the original filament voltage. And now this yellow wire supply this tube with filament. Haha, so that is a good way to get it up and running with an original tube that is not the original type, right? So anyway, I also changed one of the EF80s in the amplifier, and now the amplifier here tracks a lot better, and this is of course why we have a beam. Let's look a little bit on the schematic. This is the first page of the schematic, and it shows in the bottom left the vertical input attenuator. And the fun and really cool thing about this input attenuator is it's balanced. So you got a positive and a negative input to the balanced amplifiers. You don't need to use the inverted input, but you can if you want to. So I think that is really cool. And this gives you the opportunity to invert your input, or to, of course, transport a fully balanced signal all the way. So what we see here is a 6-tube, 3-stage balanced amplifier using pentodes, and it's DC coupled. And we got a DC gain of 2000. So obviously there's quite a lot of drift in this one. And this, you can maybe see this if you zoom in, or if you got a really big screen, but you can see here in the middle, we got some potentiometers to fine adjust the DC, both the knob on the front, but then there's also another knob hidden behind a little metal thing you pull out, and then you can access the other drift or DC offset potentiometer, and then there is a trimmer in there to handle all this. Of course, you need to retrim all this when you change the tubes and all that. And this is, of course, where I had one of my problems. I had a missing 160 volts, and this way everything here was completely out of center, and it was that is why I couldn't see the beam. In the upper right corner, we see a regulated power supply. This is a really funny thing. I should, of course, zoom in here on the power supply so we can easier see the details. There's a rectifier tube and a doubled filter choke system. And then they say a 345 volt. And look at the bottom right. Now it's only 320, but it's the same net. It's the same wire on the schematic. So what exactly are we talking about here? So that is a little bit funny. And yeah, this is just a normal dual pentode regulated supply with a voltage reference tube. And I've already explained about that one. So let's zoom in on the high voltage supply. This unit consists of two transformers, both running on mains frequency. The biggest one in the middle of the back of the chassis also powers the other in parallel with the primary input, as you see here. So they are both mains voltage input, and then you got two tube diodes, so to speak, rectifier single diodes, and this is how they're making a positive 2000 volts and a negative 2000 volts. So cathode intensity and focus, that is at negative 2000, and then the anode can be either the plus 300 volts or the plus 2000 volts, depending on where this voltage selector switch is. So this is why they say on the front you have either 2000 volts or 4000 volts on your CRT. Here is schematic page 2, and the bottom half of the schematic, that is all the sweep stuff, sweep timing, oscillators, a trigger, and all that kind of stuff. And the top right part is the X amplifier, the horizontal amplifier. And here is the X amplifier zoomed in, and it is exactly the same schematic as the vertical amplifier, but we only got two stages of amplification, of course, so much less amplification needed to handle the horizontal system. So that is definitely why. But other than that, it's exactly the same idea. No need to invent or anything new or different, because this one just works perfectly fine. So I had to dim the light to show the picture here because it's really not that bright, and I got a lot of other problems with high voltage and all those leaked capacitors removing all the high voltage. So you see, this is the 2 kilovolt setting, and there's not any difference in the intensity. And see here, it's not responding to the intensity potentiometer because that one is completely destroyed by all this oil or whatever came into that potentiometer. Focus is responding barely, and that is, of course, the voltage is not right. But we got X and Y input in XY mode like that, and you can see my little logo thingy, and we can change the amplitude. See, this is amplitude, and this one is position. And here we go with a little bit of, see, that is the amplitude right there, and then position here. So look at that, 74 years old or something like that, and I got a picture back on it, so I am a little bit proud of that. So I think I will say thank you very much for watching. I hope to see you soon again. That was some fight, and I'm not completely done. And you can see we're blinking here. It's using 200 watts at the moment, so that's a little bit too much. So I better turn off before something explode on us, and we don't want that. No more fires or anything. So yeah, that was something. It took me a million minutes to pull these damn capacitors out. And the fun thing is, they are all Zener diodes now, those capacitors. So they're full of leakage at voltage, about 600 volts, and then they become a nice regulated voltage regulator. That's what it is now. So why did that happen? I actually don't know. They're just old and real bad. I cleaned one of them here so we can really see how beautiful they are. Look at the size. Half a microfarad, 2.5 kilovolts. And they've been really bad for a long time. And that is, of course, why we see those 4 series resistors to those capacitors being really that burned. So now I found some other capacitors here. They're a little bit less the value, but I put 2 and 2 in series to obtain a good safety voltage and tape them a lot. So this is one of them, and the other one is a little bit down here. I don't know if we can see that. It's probably not that interesting anyway, but it's there. And I didn't mount the blanking capacitor yet, and I also didn't mount the 4 kilovolt supply as well, because that is not super interesting. So there's a plus 2000 volts and a negative 2000 volts, and it's only the negative 2000 volts I am playing with right now. So let's try and turn it on and then investigate here what is going on. Look at that. And this is our cathode supply. And it's of course going all the way up, and until we see a little bit of filament in the tube, it will start to use a little bit of current, and then the voltage should drop a little bit again. See, now we see the voltage start dropping. And also the power consumption is a lot more realistic. See, 170 watts more or less. And what happened here at the front, maybe we should remove we have a nice bright beam, and intensity and focus is working. It's even in focus when the knob is in the middle. All that is so good. So now I can continue to play with it. Oh, we got lots of. And this is only the 2 kilovolts. So I probably want to try and put in the positive as well, and then see what happens if we give it full. Also want to play with the sweep and all that. There's plenty of fun in this scope. It's been driving me absolutely nuts about the 160 volt supply that is just way too low. And I think there is a reason for that. I think it has something to do with stuff that uses too much current. So what I'm doing here, this is the 160 volts regulated output, and everything else here is off and ice cold. This is actually quite early in the morning, and I didn't power anything up yet, so everything is ice cold. So what I'm doing here is I input a 160 volt like that from an external power supply, current limited of course, but look at that. It's using nearly 50 milliamps. That is a little bit high, isn't it? And I know all those resistors here that makes all the different voltages and all the voltage dividers, all those kind of things, they are of course used or used to be warm. I mean, this is normal. This is not a big problem. But what I seek is a thing that gets warm that is not supposed to be warm. So how do I track that? Yes, I use a thermal camera. It seems to be a little bit like cheat mode, but why not? So everything I look at here, look at that. That will be the 2 red resistors, yes, and then I can look in the schematic. This is perfectly normal. They're supposed to be warm, and I just keep hunting. Okay, warm resistor, perfectly fine, la 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 la, all the way around here. And then I look in here. What is that? That looks a lot like this capacitor. This blue capacitor somebody put on there. This one gets warm. Capacitors aren't supposed to get warm. No. Yes, of course I just turned it on so it's not burning warm, but anything warm here is definitely a fault. So maybe this is why it's not working. All the other capacitors down here is not warm at all. Oopsie, 2 resistors, perfectly okay.